Hello, my name is Clanton. I'm a graduate student in astronomy at The Ohio State University, and I'm here today to tell you about my recent paper investigating the photometric precision limits of current generation infrared detectors. The Kepler and Corot missions have demonstrated the power of the transit method for both discovering and characterizing exoplanetary systems. The Kepler mission is finding planets around mostly faint stars in a relatively small area of the sky. Conversely, an all-sky survey would look for planets orbiting the brightest stars in the sky. A near-infrared survey to identify transiting planets, with an emphasis on cool K and M stars, would find many Earth-like planets in the habitable zone. In this polar diagram, the radial coordinate represents a J magnitude, and the polar angle represents a simulated sky coordinate. The data points are the expected planet discoveries from a simple Monte Carlo simulation, with the confirmed Kepler planets and Kepler planet candidates shown for comparison. The small filled circles are gas giants, and the red crossed circles are the rocky planets from the simulation. This figure suggests that an all-sky near-infrared survey would find hundreds of rocky planets and thousands of gas giants, many of which would lie within the habitable zone. In this paper, we report on the photometric properties of Teledyne's widely used infrared H2RG detector through a series of laboratory experiments demonstrating the technical readiness of spaceborne transit experiments using existing near-infrared detectors. By projecting an ensemble of spots onto the detector in a controlled environment, we performed experiments designed to investigate three major sources of degradation in high-precision photometry. These include long-term drifts, effects from simulated pointing drifts and offsets, and also effects from changes in the detector temperature. We decorrelate the spotlight curves against parameters that describe these drifts, offsets, and changes in the detector temperature using a principal component analysis. This figure shows the result of first averaging decorrelated light curves of multiple spots together and then computing the Allen deviation of the averaged light curve. We use Allen deviation as the main measurement statistic for assessing photometric precision, as it preferentially selects noise at a characteristic timescale, while rejecting noise on timescales both larger and shorter than this characteristic value. The various curves correspond to averaging different amounts of spots together before computing the Allen deviation. We conclude from this figure that when sufficient flux is included within the measurement, the noise falls off as 1 over the square root of time until reaching a floor of roughly 10 to 20 parts per million. Overall, our data show that by using decorrelation techniques and suitable averaging of independent samples, the H2RG can achieve very high precision differential photometry with noise values as low as roughly 20 parts per million. This demonstrates that these detectors are suitable for the high precision relative photometry that is required for an all-sky transit survey. For a complete description of our study, please see our paper posted on astro-ph.